Alright guys, here I'm going to replicate these two kind of case studies, right? The parametric precedents that I showed in lecture. One of which this is the One Ocean thematic pavilion by SOMA for the Expo 2012 in Yeosu, Korea. And the sort of kinetic facade, right? That looks like sort of shark gills, right? And or it's similar typology, but the sort of Garibaldi exhibition building in Milan, Italy by Grimshaw architects, right? So same kind of strip morphology, and these are kind of linked in our Canvas site as well, so kind of do take a look when you have the chance. But this is a file that's provided, so it is a simple rectangular surface with a little bulge in the center, right? There's a little kind of geometry to it, all right? And while this is the example we eventually link to, it may be helpful for you to make a kind of new surface right next to it that's roughly the same size, just flat, like that, right? To kind of understand or see what's going on a little bit better. We eventually will transfer things over to here, okay? So to start out with, going to geometry surface, right? We're gonna plop down a surface container, right click, set one surface to link my source geometry in, right? And the divide, right? There are a lot of different divides. The one you're looking for is the divide surface, or S divide. That's how it looks like here, right? And we'll link that in. Immediately we'll get some surface subdivisions, right? We do want to be able to control these in particular. So I'll make a slider that goes 0 to, let's say, 16, and make two of them. So copy paste. Can align them, and each one corresponding to a U and a V value, okay? So you'll kind of see how this factors in a little bit, but this, for now, I'm going to set my U count to 5 and then the V count to something like 8, all right? 5 and 8, right? Now what's this doing is on these surfaces, right, it's kind of dividing it, right, finding the sort of right, let's say, cross points, okay? Now, if I look at these precedents again, right, and the sort of basic, let's say, structure of some of these things, right, there is a sort of original, let's say, section curve, right, that's kind of lying on this surface, and then there's a, let's say, bulged out, right, section curve that's over there. So essentially we're going to use that to draw the inside, and then kind of use the same, let's say, move, right, in the Z direction to kind of get this offset, essentially, right? So these are the section curves, right, that we're looking at, and we're just going to kind of redraw them. So this is the interpolate curve. I think it's this one, right? Interpolate, create a interpolate curve through a set of points, all right? So this guy, because our outputs here, right, these are the division points over here, right? We don't need the normal vectors. These are parameter coordinates, meaning these are its addresses, right, for each point on the surface, right? Okay, but if we just do this, well, you'll see it immediately draw those lines, okay? Now we're using this, not a polyline, right? Because eventually we want these to be curved, and this will actually change if I move it over, right? It will actually follow the curvature of the surface, okay? So that's why it's important to use the interp curve right here. Now, while this gives us, right, 6 NURBS curves, so 1, 2, 3, 4, 5, 6, these are the section curves, I still want the subdivision points, right? I still actually want these points because I'm eventually going to kind of move these a little bit individually, right, in a differential way. So instead of moving the curve, I'm actually just going to take the curve and divide it again. So divide the curve again right here to get more these points. Now you'll see the points don't match, right? So that's why this number, right, this n, actually has to match back to this, right? This is the 1, 2, 3, 4, 5, 6, 7, 8, right? The count here. So if you see here, if we make these link together, then the points basically overlap because it's the same subdivision, right? So both the UV number amounts here and in my later divide actually use the same number input here. All right. Okay. So knowing what we know from previous exercises, right, we can simply use a move, right, command here and tie it using these points, right, move these points vertically, right, up in space, okay. And while it is set to a z translation vector of 10, right, by default, I usually like to pin it to the unit z like that. That'll make it only 1, right? So eventually when you do multiplication of it, it makes it slightly easier, okay? So that z vector can be multiplied, right, by something, right? And usually you just do something like this, like 0 smaller than, let's say, 20.00, whatever, right, something like that, and you just put it in front, which then multiplies the z vector, which allows us to kind of control how much this moves, right, in the z direction. Okay. Now we know that by kind of looking at this example that this sort of movement is not a simple offset, right? The offset actually changes over time or across the section. It's smaller here, it's highest there, right? So we need to find a way to actually specify this kind of offset direction, right, as a curvature. So earlier in lecture we actually talked about the graph mapper, right? And if you are not sure about that, just kind of refer back to some of the examples here. This graph mapper usage example that I showed in the beginning of lecture earlier. Okay, so the graph mapper is a really intuitive and easy way for us to work with things. So it's under inputs right here, graph mapper. Okay, and if you can kind of recall, we do need to kind of feed the graph mapper a range of values, meaning that we have these sort of set, let's say x coordinates, right, between 0 and 1 that we want to look at essentially. Okay, so what we're gonna do here first is to make a number domain. No, not this one. Construct a domain. So construct domain. Okay, and these are actually just straight values that are fixed. So a 0 value, so meaning the number domain starts from 0 and it ends with 1. Okay, so 0 to 1. All right, that will give us number domain of 0 to 1. Okay, and we'll use the number range right here, create a range of numbers. All right, now these are all kind of under maths, right? Domain somewhere over here, right? And some are actually under the set, tab. A lot of these sort of operators, right? So this one is under set and sequence. I kind of forget where they are sometimes. So series, sequence, range, right? These are all kind of ways to make like number sequences. This range right here. So first input domain, which is what we've constructed right there. And then number of steps. This is basically, let's say from 0 to 1, how many steps you wanted to divide it by, okay? And the same thing, right? We actually wanted to match this, this sort of cross-section count, okay? So that's why we're also using this value, the v count value over here, okay? And then this just goes into there. All right, now we need to set a graph type, meaning you have to click on the graph mapper, right-click, and set to, in this case, it might be Gaussian. Yep, okay. So the Gaussian sort of pattern, right, does this, has a sort of, you can kind of move the peak, you can move the amplitude, right, left and right, or up and down, okay. And instead of doing a straight up multiplication into the z vector like this, we're actually going to bring in a multiplication, normal multiplication, modifier component, right? And actually have this be part of that, have this go into there, and then have this go into there. All right. So what you'll see now is a bit clearer, because if I look at it from the side, right, essentially what you'll see is this is now kind of reflected, right, and it's amplified by the amplitude of the graph mapper. So you can kind of mess with these, right, to see, what the right, look or feel of it looks like. Okay. But that offset gives us, instead of a straight offset that's all the same across the section, it gives a differential offset that way. Okay, that's why like this is important, that okay, well this we're feeding here, what we're feeding here, right? These are actually all the same number, right? They will match regardless of how we eventually decide to subdivide this thing. Okay, all right. So now we're here. We'll actually do the same thing. We'll use another interpolate curve. So I'll just copy paste it over and feed it into here. So that is what will redraw these section curves across. Okay. Okay, so now if we just look at things and say, oh well, maybe we can try to loft some of these guys together, right? Because I know this is the bottom part, right? This is the top part. So it's actually, we're kind of looking at these two things, right? Let's say if we do this, what it actually will do is, because these are all NURBS curves, right? And let me pull the panel out to look at it. These are all NURBS curves that are kind of in their own little bubbles, right? Their own little container individual lists, right? So you can't loft a curve on itself, right? It needs a partner, right? So this won't work because of that, right? Now, even if, let's say we added in this right? It still would kind of look at these as, different, sources or different separate things. Each one is on its own. Okay, so this is why we need to use something like the flatten. The flatten tree component here is what then changes this data structure from, right, individual kind of components inside their own lists to one list, right? And so if we try to loft this, for example, then what it would do is actually it would loft through the ground curves, right? 0, 1 to 0 to 5, 0 to 5 that way in a sequence, right? It would actually do the same for this guy over here. Let me just copy and paste the flatten over, okay? It's the same here, right? It would loft through these sequentially, okay? Now, that's not really what we want here right away, okay? Because even if we combine these, it would just do these two sets separately, right? It would do this guy, which is the sort of floor part of it, bottom part of it on its own. It would do this top part on its own, right? And so that's why you end up with two like completely separated surfaces, right? So for this to work, we actually have to graft it again. So basically, both of these grafts will have to happen somewhere. And we can kind of take a look at this really quick as well. Okay. So the graft essentially kind of puts them back into sublists again, right? Just like that, right? Now, what I'm actually trying to do here between the flatten and the graft is to actually match their data types. So eventually, let's say if this graft comes out, you'll see that the way these curves, both in the top and the bottom, are labeled and numbered are exactly the same, right? Meaning that they are now, using the same way to organize the data structure, okay? Now, because of that, what happens when I basically kind of merge this, right? So you'll see nothing's happening, right? They're all in their own little sort of buckets. When I add it together, okay, now they're lofting bottom to top correctly, right? Because our data types are matched now. All right, so let's don't forget that, okay? So this is sort of, up to here. This is up to here, right? These are kind of how it should be organized, okay? All right, now our problem is, right now, is that it's doing this, but it's not going across, right? Now, to get it to go across, we just need to insert the shift component somewhere. Shift list, okay? And that somewhere actually would happen sort of in between here, right? In between here and here. So while it is still in the continuous list form, while it's still like this, let's do our shifting while there's actually a list to shift between, right? So this goes in here, 0 to 3, for example, slider, all right, integer. And what this will do, it looks the same here, right? But as I kind of move it, basically what it does, it reorders them and it kind of shifts them across, all right? So, and this is helpful, and we'll do that kind of over, okay? So what you'll see is that even if we sometimes, right, even if we add these together, right, you might not get a result out of the loft component, right? Even though these are correct, and we can kind of look at this. So linear curve, right, all in their own kind of little sets. Our hope is to match like one of these to one of those, one of these to the one of these, right, to kind of have them match across. Now, one of the reasons they're not lofting correctly is if you look at the data structure, they're different, right? So certain components deal with this differently. The loft one, right, probably just needs this actually to be a bit more matched in terms of the addresses, right? And you can refer to some of the earlier videos that kind of talk about the paths, right? This nomenclature here. But essentially what we need to do is actually kind of simplify this down to its most basic form. And that's where the simplify tree command comes in. This, let me pull it over here. So simplifies a data tree by removing the overlap shared amongst all branches, right? We also kind of said that you can use the parameter viewer, so this guy, to kind of look at it. So data with 5 branches, right? It looks like this versus the other one, right? So you can kind of see how the structure is different, that this one has an extra, let's say, stem branch before it splits out into the 5, where this one basically kind of goes out into the 5 right away, right? That's why it's the numbering scheme between these things is a little bit different, okay? So we need to get these to actually work together and match properly, right? So that's where the simplify comes in, because when we, after the simplify, it goes from that to just simple 0, 1, 2, 3, 4, right? And this changes to that, okay? And we basically would do it on both sides, right, to be able to get these to kind of match completely. All right, so that's what we're doing. Now, that being said, one of the things about this actually means that from this interpolate curve, right, which is, you know, kind of this more complex version of this, right, that has all of these, the simplified would just like pare it down to 0, 1, 2, 3, 4, 5, and we actually wouldn't need any of this stuff, right? We wouldn't need the graph, we wouldn't need the flatten. We can go from here to the simplified directly and add that, holding down the shift key to add multiple streams into one to get that loft. So this actually need to replace that, add, right, to get that to loft over, right? So the thing to check here is that, okay, 0, 1, 2, 3, this is that data structure, this is that data structure, right? So this is the same. The reason it's losing 4, or this has 1 less, right, if you kind of compare the two streams, okay, whoops, is because of the shift. So if I do this, this is the original, right, where this is lofted to that, and it has 0, 6 things in it, 6 things in it. When I shifted 1 over, okay, then we basically lost 1 from the top one, right? So that's why these ones are empty, right? We're basically kind of moving this across, right? Because we're connecting from this to here, this to there. We're connecting diagonally, and then the last one here has nothing to connect to, right? So we need to take one out. That's also part of this, the wrap values thing that's connected to the shift, meaning that, you know, if I actually had this set to true, what would happen is that we would have one of these lines actually connecting straight across to that first one, right? That, as you kind of see here, right? This big diagonal thing right there, right? So you can set a Boolean toggle onto that if you want it to be a bit more explicit, right? When it's false, that happens. when you have wrap values on, then you actually kind of try to circle back to the first one on the other side, right? So this is set to false by default just because we really don't need those guys, all right? And that is actually pretty much it for this. Now, let's go back and say, well, let's kind of relink this to a complex surface over here. I'll just delete this guy. Okay. So this surface now is able to basically bulge. It bulges in both directions, right? You can kind of change the amplitude a bit more closer. This top one changes how many subdivisions or gills ultimately it has, right? You can kind of adjust that proportionally. The V count here basically kind of changes how smooth the transition is. If I bounce it to very low, then you kind of get more rougher, right? Maybe simpler. So this is kind of more like the SOMA Pavilion, where it's really just kind of like an arc. Whereas the Garibaldi would have much more nuance in its sort of curvature and, you know, higher peaks and things like that. Okay, so this is the sort of first kind of example that I showed you guys. Now, this sort of setup has a second version of it, which I'll demonstrate here really quickly. Where, let's say, if I took this surface and I started rotating it, right, let's say to vertical, you'll see that the script kind of breaks a little just because we're relying on the z vector right here to actually do our translation, our movement, right? And because the z vector is always up regardless of which direction the surface is, so let's say if I rotate the surface that way, then the gills will go in the other direction, right? Which is kind of not super desirable, right? Because if we want to have something that can work in all directions, then we need to come up with a slightly more robust example. Okay, so that's why, and this is a small modification in the examples in the second one right here. There's a small modification I make to it, and this is sort of what we call the improved version. And so it operates regardless of the orientation of the surface, not only in the z vector direction, right? And it uses the evaluate surface component to sample the surface normal vectors at all the subdivision points and uses those as the offset direction for each point. All right, so let's try that. So evaluate surface. Okay. Now this guy. So this guy, what it gets is a base surface, right? And this base surface actually goes all the way back to our original input surface. So this guy here, okay? The UV actually are essentially saying, okay, well, where do you want me to measure, or where do you want me to give you things, right? What are the addresses, right? And as you know, the surface divide component actually gives us addresses, right, for all your subdivision points, right? So what we need to do is actually just connect these UV addresses to this UV input, and it will actually give us a bunch of these little grid things, okay? Now all these little grid things, and let me just delete this z vector right away. What all these little grid things are doing is that it's essentially kind of measuring, right, at each little grid point, what is the normal direction, right? The direction perpendicular to the surface at that point. Just so we can see this thing a little bit better, I'm going to rotate this back. Okay, and you'll see stuff has happened to the script, but that's all right. Which means that, okay, you know, at this point, right, what is the direction that's facing perpendicular from the surface? You know, at some of these points that are kind of bulging outwards, and those would be that way, the ones over here would be that way, right? So it really depends on the local curvature, right, of that overall surface, okay? And it gets really kind of pretty simple. Is basically this kind of sits in between here, right? We just need another multiplication. So add another multiply in between here and our move, okay? And what happens here is that we don't want the points, we want the normal directions, right? These are kind of normal vectors, right? And so we're already working with vectors down here, right? This is, you know, kind of working with the idea of vectors. So we're just adding the vector in as a multiplication to here, and then using that to there, okay? So let me hide these, and what you'll see is that, okay, it's now back to normal, right? We're only inserting kind of these two guys, right? These are the only two different things in here. Compared to the earlier one, we're just replacing the z vector and inserting these into here. Now, what's really nice about this is now that because it's based on the surface itself, let me kind of tone this down a little. Because it's based on the surface itself, I can kind of now rotate this even upside down, and it's still offsetting, right, in the right direction, regardless of where the orientation of the surface is facing. So it's a much more kind of robust solution. All right, that's it.